Hello everyone. Today we are going to look at the notes for section 15.1, which is going to talk about the physical properties of sound waves and how they are similar to other waves and how they are specifically related to how we perceive the sound. So we're going to start, as we often do, with some vocabulary terms. Hopefully these are familiar to you. And as I go through these, you can think about, did I know that? Was I just waiting for her to write them down? Am I copying? Am I thinking? Okay, so frequency. The frequency is the number of cycles, but we're going to say waves because that's what we're talking about, per second. Right, and our formula, F, lowercase f is frequency, is equal to 1 over the period, or we can have frequency is equal to the velocity over the wavelength. Frequency is always in hertz. Amplitude. So amplitude, remember, is how big the wave is, right? The distance from equilibrium. All right, we don't have a formula or anything for that. Wavelength. This is one of those ones that's self-defining, but we'll write it down anyway. So wavelength is the length of one wave, right? And if we want to find the wavelength, we're going to say wavelength is velocity over frequency, or we could also say wavelength is velocity times period. We measure wavelength in meters because it's a length like any other length. Our last word today is velocity. You should really know this one. The velocity is the speed, this specifically in this chapter, it's the speed of a wave. And our velocity formula, we have two here we're going to look at. Velocity is distance over time, or velocity is wavelength times frequency, and of course velocity is in meters per second. Okay, hopefully those were all familiar to you. If not, you need to make sure you go back and know them before we take a test. All right, so sound basics. Sound, of course, is a wave, and it has some similar things to waves we've looked at, and in some ways it's a little bit different from waves that we've looked at. Sound is a longitudinal wave which means it has those areas of compression and expansion, right? Okay, longitudinal waves. It's hard to look at a longitudinal wave, so we're going to draw our sound waves as transverse waves, even though we know they're actually longitudinal. They're a little bit easier to interpret that way. Just like with all mechanical waves, sound needs a medium to carry it. When I say medium this time, I do not mean the size between large and small. What I do mean is that it has to travel through something, right? It has to travel through a spring or a string or something that is going to carry that energy. In our classroom, the medium that carries the energy is the air, right? So if you are talking in our classroom, the way the sound gets from you, your mouth, when you produce it, to somebody else's ear is that it has to travel through the sound, or through the air, excuse me. That's the medium that's carrying the sound. Okay. Sound also, by the way, will travel through liquids like water, and it will travel through solids like steel. And those things have an impact on how the wave moves, but we'll talk about that a little bit later on. All right, so sound has some important characteristics, and the first characteristics of sound that we're going to talk about is the volume. Volume, of course, is how loud or quiet a sound is, and one of the properties of sound is what makes it be a loud sound or a soft sound. So I'm going to draw a loud sound here. I want you to draw it too. So here's our loud sound. I'm also going to draw a soft or a quiet sound. All right, and I want you to look at those for just a minute and tell me what's the biggest difference between the loud sound and the soft or quiet sound. All right, and hopefully you notice that the biggest difference here is the amplitude of the sound. So a loud sound has a large amplitude wave. That means it has lots of energy in it. When you're, someplace and you're really excited and you're shouting and yelling, you're putting a lot of energy into that sound, and it's a loud sound. It has a big amplitude. On the other hand, when you're sitting in a classroom and you don't want the teacher to hear what you're saying and you're just whispering, this is a very soft sound, right? It doesn't have a very big wavelength, it doesn't have a very big amplitude, and it doesn't have a lot of energy in it. So when you think about the amplitude of a sound wave, I want you to associate that with the volume of the wave. All right? Next characteristic is pitch. So the pitch, if you are a music person, you already know this. The pitch of a sound is the highness or lowness of the sound. So I can talk in a really high-pitched voice, or I can talk in a really low-pitched voice, right? And that has to do with how the sound waves are generated. And a high-pitched sound is going to look like this. A low-pitched sound is going to look like this. All right, again, I want you to take a look at those two drawings and decide for yourself what is the biggest difference between the high-pitched and the low-pitched sound. Okay, hopefully you notice that the biggest difference here is the frequency of the sound. If I have a really high-pitched sound, I have lots of waves that are really close together, and that gives me a high frequency and a high-pitched sound. On the other hand, if I have a low-pitched sound, these waves are really spread out. They have a low frequency, and a low frequency means a low-pitched sound. So when you think about the pitch of a sound, I want you to associate that with the frequency of the wave. All right? So we have looked at the type of wave sound is. Sound is a longitudinal wave. We've looked at the medium that can carry the wave. We've looked at what volume means and what pitch means and how those relate to wave characteristics. So I want you to turn off the recording for about 30 seconds or so and write me a sentence here. How do the properties of sound waves relate to our perception of sound? Okay? Turn the recording off, write your sentence, and then I will meet you back here shortly. All right. So we talked about the type of wave. Sound is a longitudinal wave. We talked about the mediums that can carry sound. We talked about the volume and the pitch. And now we're going to talk about the velocity or the speed of the sound. Okay? So just like any other mechanical wave, the speed of a sound depends on the medium. The medium the sound is traveling through. So we talked about the fact that most sounds that we are accustomed to hearing travel through the air. We usually do most of our hearing right when our head is in the air. Sound can also travel through water and through steel and through all kinds of things. But usually we are used to hearing our sound traveling through the air. Sound traveling through the air has a velocity of 343 meters per second. That's really fast, actually, right? If you were standing 343 meters away from someone and they yelled at you, you would hear the sound 1 second later. That's pretty fast. Okay, since sound is a longitudinal wave, it travels faster through more dense mediums. Now, this is real similar to the springs that we looked at on the floor last week, right? We said that the wave traveling through the snaky or the really skinny spring traveled faster because those wave coils or those spring coils were more closely more dense and more closely packed. That's what I'm trying to say. All right, that's true with sound waves as well. The more densely packed the molecules in something is, the faster the sound is going to go. All right, so sound in air we know is 343 meters per second. Sound in water goes up to 1,480 meters per second, and that's fresh water. Salt water goes even faster because you have those salt molecules in there. Sound traveling through steel, right, metal, is 16,500 meters per second. That's amazingly fast. Okay, you might be familiar with sound in the water if you've ever gone swimming, right? You put your head underwater, you can still hear things. Submarines use sound in the water. They call it sonar, right? You send out a sonar ping, it travels through the water, it bounces off something, travels back to you, you know how far away the thing is. And steel, so in old cowboy movies, you might have seen this, the hero, will put his ears on the railroad track and then we'll know how far away the train is, right? And that's actually true. That works because the sound of the train coming travels through the steel so fast that the cowboy can hear it faster through the train tracks than he or she could through the air. Okay, so now what about music? Well, music is an instrument that is designed to take advantage of those characteristics of sound, so of pitch and of volume and of speed, right? The instrument takes advantage of all of those things. And musical instruments are designed to vibrate with different frequencies, and those different frequencies create the different notes that we hear. Every instrument has a part of it that vibrates, and that part transfers the vibrations to the air and eventually into our ears. So any instrument you can think of, you should be able to decide what it is that's vibrating on that instrument that's creating that sound. All right, so I have some examples here. So those of you, again, that are musically inclined, you already know the answers to all these. What vibrates in a clarinet? So in a clarinet, there's a reed in the mouthpiece here, and as the person is playing, they blow across the top of the reed, and the reed starts to vibrate, and that's what causes the sound of a clarinet. How about a piano? What causes the sounds in a piano? If you have ever opened a piano, you know that there's piano wire inside of it, and as you play the keys, there's a little hammer that hits the wire, and the wire starts to vibrate, and that's the sound that we hear. How about a drum? The drum has a head and a membrane, that's the top part there, that vibrate, and that's what causes the sound that we hear. And actually a drum is a really good example of pitch, because if you have a small drum, you're going to have a really fast vibrating head and membrane, and so you're going to get a high-pitched sound. You have a great big bass drum, right? It's huge, it doesn't vibrate very quickly, and so you get a lower sound from that. All right, of course we can determine which notes, particularly wind instruments, will play if we know how long the instrument is. In other words, how far the air has to travel to go through the instrument. That's what helps us to know what notes that instrument can play. And we also need to know if the air is traveling all the way through the instrument, like in a clarinet where the air goes in one end and out the other end, or if it goes into the instrument and bounces off the other end. So here's our example. This person is blowing across the top and into this plastic, maybe it's a water bottle there, and that creates a sound. If you've never tried this, go find a plastic bottle sometime and blow across the top of it. It makes a sound. And depending on how much liquid is left in the bottle, you can change the pitch of that sound. So what's the air actually doing as it travels into that bottle? So what is the air is actually doing? You blow, the air goes in, travels down the length of the bottle, bounces off the bottom, and then travels back up to the top of the bottle and out through the same hole it came in, right? And so the air is not just traveling like in a clarinet, right, all the way through. The air is going in, bouncing off the bottom of that bottle, and coming out again. So if we want to find the lowest frequency that this, we call it a closed pipe resonator, that this closed pipe can play, we would need to measure the length of the air column. And the different lengths of the air column will give us different notes. Our formula that we're going to use here is F equals V over 4L. I should have made this a little bit smaller here, sorry. Okay, in this case, V is going to be 343 because we generally play our instruments in the air, and so that's what the sound is traveling through. And L here is going to be the length of the air inside the instrument. And we want to make sure that our air is in meters, right? Because we're going to have meters per second for our velocity. And then F, of course, is the frequency. Often you'll see it written as F1 because it's the lowest frequency that that particular instrument is going to play. Okay. All right, so let's do an example here. We've got a test tube that's 15 centimeters long and has 3.5 centimeters of water in the bottom. Calculate the lowest note that this instrument can produce. All right, so what are we going to need to know? We're going to need to know the velocity, which is 343 meters per second. By the way, that's a number that I do expect you to memorize and or have on your note card, the speed of sound in air. We also need to know the length of the air column. So let's take a look here. This problem told me that my test tube was 15 centimeters long and that this bit of water in the bottom is 3.5 centimeters. And what I want to know for my formula is what's the length of the air column. So how are we going to figure that out? You are so smart. We are going to say 15, that's the whole length, minus the 3.5, which is the water, and we're going to end up with 11.5 centimeters. All right, so this length up here of the air column is 11.5 centimeters. Now, we also need to change that to meters, so we're going to divide it by 100, and we're going to end up with 0.115 meters, and that's the number we're going to use in our problem. Okay, so our length is 0.115 meters. If you don't get how we got that number, then go back and listen again. And we're looking for the lowest frequency that this instrument can produce. All right, so I'm going to say F equals 304. Nope. Forgot to write the formula. My bad. Here we go. F equals V over 4L. So F is 343 over 4 times 0.115. F equals 343 over 0.46. If you're going to put this in your calculator all at once, put parentheses around the top and the bottom because you want it to divide at the end. All right, and then when I divide this out, I'm going to get 745.65. I have to round that to just 2 significant digits because of the 15 and the 3.5. So this is going to become 740 hertz. If you are curious, that is about an F sharp. All right. So this is the end of the required notes. If you would like to continue to listen, I am going to do the rest of these practice problems here. So if you like to know how to do the practice problems, you can keep listening. Otherwise, you're going to turn the recording off. You're going to go up and get the page of purple practice problems from the sub, and you are going to work on those. All right? If you have any questions, we'll spend some time next class answering those questions. You're going to hand those purple problems in before you leave today. I want to know how much work you got done. Okay? All right, so if you're going to continue listening, here we go. Number 1, you are standing 35 meters across a parking lot from your friend. You see your friend slam the car door, and 0.102 seconds later, you hear the sound. Calculate the speed of sound as it crosses the parking lot. All right. So we know that we have a distance of 31 meters. We know that we have a time of 0.102 seconds, and we'd like to know the velocity of this sound. Now, we're not stupid, so we already know the velocity of sound in air is 343. We're going to see how close we get here. All right, so I know velocity is distance over time. I'm going to say 31 over 0.102, and I'm going to end up with 343.13. That's pretty good, right? Not going to really complain about that. We have to have 2 significant digits, though, so we're going to say 340 meters per second. Not too bad, huh? I like this formula. That's our very first formula. Problem number 2. The speed of sound in salt water is 1,535 meters per second. That's probably going to be important. A boat sends a sonar ping straight down, and here's an echo back 3.25 seconds later. And the first it wants us to draw a picture. Okay, here's my boat. Here's my water. Here's the sound going down. Here's the sound coming back up. I know that in order for it to go down and back up, it takes 3.25 seconds, which means that half of that time it's going down and half of the time it's coming back up. Do you agree? Okay. So I'm going to do 3.25 seconds divided by 2 and get 1.625 seconds to go down and 1.625 seconds to come back up. I don't know if that's going to be important or not, but let's find out. Okay, then it says calculate the depth of the ocean. So I want to know how far it is from the boat down to the bottom of the ocean. I don't want to know how long it takes to come back up. I only want to know how far it is to get down. So I'm going to use my velocity, 1,535 meters per second. That's really fast. And I'm going to use my time, 1.625 seconds. Do you know why we're using 1.625? Yep, because it's half. Good for you. And I'm going to take my formula and rearrange it so I get distance is velocity times time. 1,535 times 1.625 gives me a depth of 2,494. How many significant digits can I have? Good for you. It's 3, right? Because 3.25 seconds has 3 significant digits. So this is going to be 2,490 meters. So far, so good? Okay. Last one. Water fills up a test tube so only 5 centimeters of air is left at the top. Calculate the frequency of the note produced by blowing across the top of this test tube. All right. So we know a length of 5 centimeters. We know the speed of sound in air is 343 meters per second. And we'd like to know what note this test tube is going to play. Well, I'm going to change my centimeters to meters, so I'm going to get 0.05 meters. And then I'm going to say frequency, lowest frequency is velocity over 4L. So V is 343 over 4 times 0.05. Frequency is 343 over 0.2, which is 1,715. Everybody okay? How many significant digits can I have here? Yep, just 1. There's only 1 in 5. So we're going to make this be equal to 2,000 hertz. Okay, well, thanks for sticking with me this long. As your reward, number 2 here, that's going to be the extra credit question on the test. Just saying. Okay? You also now are going to go get that page of purple practice problems from the sub, and you are going to work on it with or by yourself or with a partner. It's up to you. And you are going to turn it in before you leave so I can see how much you got done. Thanks so much, and I will see you soon.